All right, you are welcome again. I trust you are doing well. Okay, now let's take a look at this under Laplace. Let's take a look at this, which is one of the properties of Laplace integral transform. This property is called first shifting principle. Okay, first shifting principle. Let's pay attention and grab this. Okay, now the theorem says if f of t has a Laplace transform f of s, where s is greater than k, then e raised to the power of at f of t has a transform f of s minus a, where s minus a in bracket is greater than k. Okay, now in a short form, this is what this theorem is talking about. It said that the Laplace transform of e raised to the power of at multiplied by f of t is going to give you f of s minus a. Now, I want to explain this and then at the same time prove this, okay? I'm going to explain this, prove it, and give some examples. Please, let's follow gradually, okay? Now, to prove this, if it is true, from definition of Laplace, we say that the Laplace transform of f of t is given as f of s, the integral from 0 to infinity e raised to the power of minus st f of t dt, where t is greater than or equal to 0. Okay? Now, if this is true, this is the definition, right? And we know it's true, right? Good. Now, what if this f of t is being multiplied by a function e raised to the power of at? Okay, what if it's multiplied like this, where we have the Laplace transform of e raised to the power of at f of t? In a case like this, what are you going to do? Now, using this definition, that means we are going to have the integral from 0 to infinity e raised to the power of at multiplied by the main definition of Laplace transform of f of t, which is e raised to the power of minus st f of t dt. Hello, I don't know if you understand this, right? Now, take a look at the definition, Laplace transform of f of t, and now the Laplace transform of e raised to the power of at multiplied by f of t. So we just added e raised to the power of at to the integral, right? Good. From here, what we need to do is to apply the law of indices. Okay, now applying the law of indices, meaning we are going to add their exponents, like their powers, right? Now adding their powers, now we are going to have e raised to the power of a minus s in bracket t. We are adding their powers and then factoring out t. Okay, we added their powers and we factor out t. So when we do that, we have e raised to the power of a minus s in bracket t f of t dt, right? Good. Now, let's do it properly. Let's do it properly because the definition of Laplace transform, we have e raised to the power of minus st. So let's factor out minus so that it will look like the definition. So factoring out minus, it means that we are going to rearrange, okay? We are going to rearrange this exponent, meaning we are going to have minus open bracket s minus a close the bracket t. Now, if you take a close look at this, you will agree with me that it is the same as the above. So we have not done anything magical here, okay? So take a look at this. It's just a rearrangement, okay? Now look at this. You remember that the Laplace transform of f of t is integral from 0 to infinity e raised to the power of minus st f of t dt, which is given as f of s. Hello, which is given as what? F of s. Now, in this case now, comparing these two equations now, comparing these two, we can see clearly that s is equal to s minus a. Hello. S is equal to what? S minus A, comparing both of these Laplace. Okay, so if it is true, we see that the Laplace transform of f of t, which gives us the integral from 0 to infinity e raised to the power of minus st f of t dt, right, which gives us f of s. So in place of this s now, we are going to write what? S minus a, because s is equal to a. Hello. So when we do that, we are going to see that the Laplace transform of e raised to the power of at f of t is the integral from 0 to infinity e raised to the power of minus open bracket s minus at f of t dt is f of s minus a. Hello. So this is the proof for the first shifting principle. Now, I chose to explain this principle using series of examples, using some examples. Now, let's take a look at this. So I want to solve this. So at the end of solving these 6 questions, I doubt if you will be confused. When we solve the first one, solve the second one, solve the third one, you should understand what we are doing. You should understand the concept. Okay, now let's dive into it. Number 1 said f of t is equal to e raised to the power of minus 2t sine 3t. Hello. F of t is e raised to the power of minus 2t sine 3t. Are we together? Good. Now, let's take a look at this function. We have a function sine 3t being multiplied by e raised to the power of minus 2t. So anytime we have a function like this that is being multiplied by e raised to the power of at, or where a can be anything, there is a way we do it. Okay, so first we are going to take the Laplace transform of these individual functions. Okay, we are going to take their Laplace transform. Let's go. What is the Laplace transform of e raised to the power of minus 2t? The Laplace transform is going to give us 1 all over s plus 2. Hello. It's going to give us what? 1 all over s plus 2. Good. Now, what about the Laplace transform of sine 3t? The Laplace transform of sine 3t, what is it going to give us? We are going to have 3 all over s squared plus 3 squared. Are we together? I think you know the Laplace transform of basic functions or elementary functions, right? Good. Please, if you are not familiar with this, we have Introduction to Laplace where we treated so many examples. Okay, you can visit that from our video. Okay, now let's go. Now, this principle is saying that whenever you have a function being multiplied by e raised to the power of at, where a can be anything, right? Good. He's saying that the Laplace transform of that e raised to the power at, the denominator, which is s plus or anything, right? We are going to consider it and plug it inside the next function of it anywhere we see s. Hello. Anyway, we do what? We see s. Good. Now look at it. We have the Laplace transform of e raised to the power of minus 2t, which gives us 1 all over s plus 2. We consider this s plus 2, x plus 2. Now, in the next function, which is Laplace transform of sine 3t, anywhere we see s, that is where we are going to insert this s plus 2. Hello. Meaning here, we have 3 all over s squared. In this place, we have s. That is where we're going to insert our s plus 2. So when we do that, we say that the Laplace transform of e raised to the power of minus 2t sine 3t is equal to 3 all over 3 all over s plus 2 in bracket squared plus 9. Hello. So here we say that the Laplace transform of e raised to the power of minus 2t sine 3t is equal to 3 all over s plus 2 in bracket squared plus 9. Hello. Are we together? Now let's take a look at the second one. From here, I think you will get this better. Now let's go. In the second one here, we have the f of t is e raised to the power of minus 3t multiplied by t raised to the power of 4. Hello. Now, let's take their Laplace transform, their individual terms, right? So the Laplace transform of e raised to the power of minus 3t, what is it giving us? It's giving us 1 all over s plus 3. Hello. Good. The next term, or the next function, which is t raised to the power of 4. What is the Laplace transform of this t raised to the power of 4? It is 4 factorial all over s raised to the power of 4 plus 1. Okay? Now, when we say 4 factorial, we are talking about 4 times 3 times 2 times 1. So, 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24. So, 4 factorial is 24 all over s raised to the power of 4 plus 1, which is 5. Now, look at this. We found the Laplace transform of these two functions, which is the Laplace transform of e raised to the power of minus 3t and the Laplace transform of t raised to the power of 4, right? Now, in this e raised to the power of minus 3t, look at the denominator where we have s plus 3. So we are going to pick this s plus 3 and insert it into the next function anywhere we see s. Okay? Now, in the next function where we have t raised to the power of 4, which is 24 all over s raised to the power of 5. So in the place of this s, you are going to insert this s plus 3, meaning that the Laplace transform of e raised to the power of minus 3t multiplied by t raised to the power of 4 is equal to 24 all over s plus 3 close bracket raised to the power of 5. Hello. Good. So this is the Laplace transform. Now, number 3. Number 3, we have f of t is equal to e raised to the power of minus at cos bt. Laplace transform, okay, of this guy. Now, let's take their individual Laplace transform, okay? Now, the Laplace transform of e raised to the power of minus at is going to give us 1 all over s plus a. Hello, are we together? Good. Now, let's take a look at the Laplace transform of the next function. The next function we have cos bt. What is the Laplace transform of this? It's going to give us s all over s squared plus b squared. Okay? It's going to give us s all over s squared plus b squared. Now, let's consider this, the Laplace transform of this e, okay, where we have 1 all over s plus a. Consider this s plus a. So we are going to pick this s plus a and insert into the next function. Anywhere we see s, we are going to insert s plus a. Are we together? Good. Meaning, here we have the Laplace transform of cos bt is s all over s squared plus b squared. Anywhere we see s, we are going to write s plus a. Are we together? Meaning that the Laplace transform of e raised to the power of minus at cos bt is, in the numerator we have s. We are going to write s plus a. all over in the denominator we have s squared. In place of s, we are going to write s plus a squared, then plus b squared. Hello. Yes, this is the principle of first shifting under the properties of Laplace transform. Now let's take a look at number 4. Number 4, we have f of t is equal to e raised to the power of at multiplied by t raised to the power of n. Okay, now let's do it. When we find the Laplace transform of e raised to the power of at, it's going to give us 1 all over s minus e. Then when we find the Laplace transform of t raised to the power of n, we're going to have n factorial all over Sn plus 1. Good. In this place where we have Laplace transform of e raised to the power of at, and we are going to consider the denominator s minus a. So in the next function, anywhere we see s, we are going to replace it with s minus a. That means that the Laplace transform of e raised to the power of at multiplied by t raised to the power of n is going to give us n factorial all over, in this place where we have s, we're going to write s minus a in bracket raised to the power of n plus 1. Hello. Good. Now let's go. Number 5. Number 5, we have f of t is equal to e raised to the power of t open bracket t plus 1 in bracket squared. Okay, e raised to the power of t open the bracket t plus 1 close the bracket raised to the power of 2. Okay, now what do we do here? First, we have t plus 1 squared. Let's simplify this. Simplifying this is the same thing as saying t plus 1 in bracket multiplied by t plus 1, right? Now when we multiply this, we are going to have t squared plus 2t plus 1. Hello. We are going to have that t plus 1 squared is the same as t squared plus 2t plus 1. Remember, here we are being multiplied by e raised to the power of t, meaning we are going to have e raised to the power of t open bracket t squared plus 2t plus 1. When we multiply it, we are going to have e raised to the power of t multiplied by t squared plus 2e raised to the power of t multiplied by t plus e raised to the power of t. Now, I think we have done justice to this, right? I want you to go ahead and then simplify this further, okay? Find their individual Laplace transform and then apply the principle, okay? Now, please, I want you to try it. Try it, okay? Now, let's take a look at number 6. Number 6, we have f of t is equal to e raised to the power of minus t cos squared t. Hello. E raised to the power of minus t cos squared t. Now let's go. Let's take their individual Laplace transform. The Laplace transform of e raised to the power of minus t is 1 all over s plus 1. Hello. Are we together? Yes. Now let's go. The second function, which is cos squared t. What is the Laplace transform of cos squared t? So the Laplace transform is going to give us s squared plus 2 all over s open bracket s squared plus 4. Please, if you are confused on how we get this, I have videos. We have lessons on this, particularly on this, okay, where we solve cos squared t, sine squared, and cos squared and sine squared, okay? Please check on our page, on our YouTube channel. You're going to see the lessons where we explain them in details. Please search them and watch, okay? Now let's go. So combining these two together, where we have Laplace transform of e raised to the power of minus t multiplied by cos squared t. Okay, so you remember we pick the Laplace transform of e raised to the power of at. Here we have e raised to the power of minus t. The denominator here is s plus 1. We are going to pick this s plus 1. In the next function, anywhere we see s, we are going to replace it with s plus 1. Are we together? Good. Meaning, in this place we will have s squared plus 2 In place of x, you are going to have s plus 1, close the bracket, squared, then plus 2, all over. Here we have the denominator, we have s, meaning we're going to have s plus 1, close bracket. Here we have s squared plus 4. In place of x, in place of s, we are going to write s plus 1, close the bracket, squared, then plus 4. Hello. So therefore, the Laplace transform of e raised to the power of minus t cos squared t is going to give us s plus 1 in bracket squared plus 2 all over s plus 1 multiplied by s plus 1 squared plus 4. Hello. Please, I want you to pay attention to this lesson. Go through it over and over again. And if you have any question, you can ask us, okay? Thank you very much for watching. If you are new to our YouTube channel, please do well to like, share, and also subscribe. Thank you very much and stay blessed. Thank you.